Okay, good morning, Astronomy 1020. Welcome to our second week of lecture. Today we're going to do lecture 2, part 1. You're going to learn about the nighttime sky, how stars rotate, and we're going to do coordinates, stellar coordinates, so that we can have an intelligent discussion about how stars rise in the east and set in the west, and how that might change depending on what place on Earth you are. For our lab today, we've got a lovely little lab on the celestial sphere. We're going to use this bad boy over here to identify some of the most famous stars and constellations in the sky. We're going to find the 10 brightest stars by looking up their stellar coordinates. It's a really cool lab when you do it in person. So, you know, we'll do the best we can remotely, but it's not the same as doing it in person, but we'll have as much fun as we can. To that note, I should make sure that I print out the lab today before we get carried away. And in fact, this might be a good idea for you guys too. Let's share screen. Let's go over to Blackboard here. And you guys can find the printout for Lab 2 under your Lab tab on the left. If you want to, I left a docx version in case people want to try to fill it out, like using Microsoft Word. But the way I like to do it is I like to print. We only should need the first 2 pages if you want to save yourself some printer paper. So I'm going to hit print, and for pages, I'm going to hit custom 1-2. And I'm just going to get going on that now. So you guys might want to do the same. I know some of you take a little while to get your stuff printed out.
Professor, I'm having a little bit of deja vu right now.
Sorry, you're having a little what?
A little bit of deja vu. I feel like I did this with you.
You did. And that's because in my Astronomy 1010 and 1020 class, they are both astronomy courses, and they share some common basics. In class, you're going to branch off into the solar system, and in this class, we branch off into stars and galaxies. So okay. I've done my best to make sure that there are some subtle differences between 1010 and 1020, but today's lecture, dealing with the fundamentals of the local sky, it's going to be quite similar to your lecture for 1010, because both of these courses need those common background basics. In order
all right, sounds good. I was tripping for a moment. I thought I was tripping.
Sure. What other students who've taken both courses at once have told me is that it's actually quite nice because the repetition helps solidify it a little better. Sometimes things start to make sense like the second or third time you hear them. You know, that's how life works. So the rest of you hang on to your hats. We're going for a little ride here today. Let's get into some notes. We're going to start today by talking about the orbit of Earth. So our first set of notes today are going to be on Earth's orbit. And we're going to start with a couple of basic things that you sort of already understand. Now, I can't remember actually, did we do this? We might have done a little bit on Earth's orbit. Did we talk about like the axis spin of Earth and defining counterclockwise in space? Okay, that's good. And actually, sorry guys, I'm getting you confused with 1010. I think in this class, we at least got as far as 4 key points in orbit, and we defined the spring equinox and the summer solstice. Caitlin and Paige are saying yes. Okay, that is actually wonderful. So let me take this back for a second. You know, we did have a homework problem last time on making a scale model, and I really wanted to do a little something on that. But I think I'm going to save the scale model for the end because it's more important that we get through our angular coordinates today. So let's see what we have time for. But I've got this lovely little module on, do you have what it takes to teach art, where we use our dimensional analysis skills to figure out a scale model of the solar system. I really love that module. But because we need to get to the equatorial coordinate system for our lab today, I think I'm going to start with the angular coordinates. So what we're going to do is we're going to start by reimagining a model of the nighttime sky that's similar to the one imagined or understood by Greek astronomers. Greek astronomers who subscribe to a geocentric universe They believed Earth was the center of the cosmos, and that the nighttime sky and the stars in particular were affixed to a crystalline ball which rotated around Earth. And while this is not true in reality, in fact, it's a useful lie. And it's more helpful to think about the nighttime sky like this when you first start to learn how things work. After all, when you stand out in a field at night and you look up, you don't feel like you're moving. You feel like the nighttime sky is rotating over your head. And believe it or not, being on a spinning sphere and watching stars rotate overhead is actually a little more complicated than you might think. It takes a little bit of training to understand that. So the first thing that we're going to do is we're just going to define a model of the sky similar to that globe that I just showed you, and that's called a celestial sphere. So here are some notes that we can take on the celestial sphere. The celestial sphere is a useful lie, okay? It's better than the truth, as lies often are. And if I had to define it, I would define it as a sphere of infinite radius on which things like stars, planets, the sun, the moon, galaxies, anything that goes bump in the night seems to rotate. And if we look at a quick slideshow, I'll get back to those notes. I know you guys are taking them here or writing them down. Let's see if I can find my celestial sphere here. Come on, baby. Where are you? Okay. If this is a model of the celestial sphere 48, then we can define a few key points on the celestial sphere. Maybe we'll even try to draw this. We have Earth in the center of this crystalline ball. We're not going to worry about the distances to the stars. That's a very complicated topic. We won't get to discuss that until about halfway through the semester. Right now, we imagine that they're all stuck to this sphere that's rotating around Earth, okay? If we do this, we can define a few useful points. So let's draw Earth in the center, and I'll, draw Earth's equator. Here's the North Pole, and here's the South Pole. And I'll try to imagine this large celestial sphere around it. And we can trace the North Pole up to the top of the sphere. We'll label that NCP. Trace this South Pole down to the bottom of the sphere. We can label that SCP. And then we can also make a ring around the center, which is the projection of Earth's equator. Sorry, my art skills are a bit weak today. And we can define these points as the North Celestial Pole. And again, you're going to see me use the abbreviation NCP for North Celestial Pole because astronomers love their acronyms, okay? We have the celestial equator. And I can define these things in a moment if it's not obvious, which I will abbreviate as CE in subsequent diagrams. And then, of course, we have a South Celestial Pole, SCP, okay? As for definitions, if they are necessary, I like to put it as the North Celestial Pole is the projection of the North Pole onto the sky. And I think it's helpful to think about that these are points not only on some imaginary spherical globe, these are points on your nighttime sky that you can identify if you're an observer standing in a field. The celestial equator is the projection of Earth's equator onto the sky. Of Earth's equator onto the sky, and similar for the South Celestial Pole. It's the projection of the South Pole onto the sky. Jot all that down if you can. Hey guys, there's a famous object located at the North Celestial Pole. Do we know what that is?
It's a star.
Hmm?
It's a star.
Correct. What's the name of that star?
Polaris.
That's right, Polaris. So let's just pretend for a moment like this is the astronomy class that you thought you were going to take, the one where I tell you these are the names, the constellations. And okay, so if you want to know a little practical astronomy here, which I do aim to teach, and this lecture is actually part of that, function F583. Many of you might be familiar with a asterism called the Big Dipper, okay? The Big Dipper is actually part of the constellation Ursa Major, the Big Bear. And this handle of the Big Dipper is the tail of the bear. And the flycatcher here is kind of like the butt of the bear. But it's a huge constellation that has a snout and some claws. Most of those stars are a bit fainter. The two stars at the front of the flycatcher are called the pointer stars. And they make a line in space which roughly points towards Polaris. Now, Polaris is not directly over your head, not unless you're Santa Claus, okay? For Rhode Islanders, it's certainly not over our heads. And it's not the brightest star in the sky. It's actually a somewhat, well, depending on the time of month, it can be a somewhat dim star that's noticeable, but doesn't pop out as the first star you see at night or anything. So that's what the pointer stars are helpful for, to help you point towards Polaris. Polaris is actually the tail of the Little Dipper, which is a part of Ursa Minor, the Little Bear. But unless you're living in a very dark sky somewhere in South County or Block Island, it would probably be very difficult for you to see all of the Little Dipper. From the Margaret Jacobi Observatory at CCRI's campus, I can clearly see Polaris with my naked eye, and I can see this star Kochab, and I forgot what that one's called, but I can see him too. But I cannot see these stars from Warwick Sky. And I know what I'm looking for, and it's very difficult. Like I said, in a slightly darker sky, you'd probably be able to see this. But the Big Dipper is familiar to many of us because all of the stars are quite bright and therefore easy to see. See if you can go out and find Polaris sometime. It's a good little exercise. Polaris turns out to be a variable star. That's something we'll learn about later on in our class. And that means its brightness or its magnitude fluctuates over the course of about 30 days. And you can actually see its period of oscillation with your naked eye if you keep a careful record of it. Okay, so I often use Polaris as a placeholder for the North Celestial Pole, although in reality, they're not perfectly aligned with one another. For the purposes of this class, we can mention Polaris being there at the North Celestial Pole. Before we leave this little module behind, I have one more very important note for us to take about it. And I want to start by writing this down as a special bullet point. And it goes like this. You can always see exactly 1/2 of the celestial sphere. Sorry, I'm going to have to erase a little bit of this here. You can always see 1/2 of the celestial sphere on your local sky. And local sky is a buzz phrase today, okay? This needs to be taught because this is not an obvious point. This is not an obvious statement the first time you learn it. Let me show you why with a helpful diagram here. Let's go over to a diagram of the celestial sphere, which I have here. Just a moment, just a moment. Here it is. Okay, slide 49. So let's say you're an observer standing where the yellow arrow is, okay? One tends to think of themselves as a little dude standing on a very big Earth. And you imagine sometimes that the sky that's over your head is kind of a little dude sky that's localized to your position on Earth. But in reality, that little sky that you think is hovering over your head is actually a big sky. In fact, your local sky consists of all of the stuff that you see in green here. everything in green, 1/2 of the celestial sphere, is part of your local sky. The reason why it's not obvious that that is true from a picture like this is because this picture artificially inflates the size of Earth relative to the infinite radius of the celestial sphere. In fact, if we were to draw this picture right, does anyone mind if I erase this here? Okay. And I'll do this very quickly. But if you were to actually draw the picture properly, Earth would be no more than a microscopic dot in relationship to the epic radius of the celestial sphere, such that if your head were pointed at some location on Earth, say there is essentially no difference between a line through the center of Earth and a line through your feet projected towards the horizon. So in fact, an observer pointing in that direction on Earth would have all of this as part of the dome of their local sky, 1/2 of the celestial sphere. This, of course, presumes that there are no buildings or trees or rivers in the way, which oftentimes I don't know why I said rivers, but buildings or trees or mountains are in the way. Rivers don't tend to block the sky like that. In Rhode Island, we're often surrounded by hills and buildings in such a way where a good fraction of the sky is cut off to us. But if you've spent any time out in the desert, say out in Tucson, where I went to college, you really, or if you've been at sea because you're a sailor, you get an experience of this big dome of the sky that's really magical and special. And it's a worthwhile experience if you've never had that before. So for the most part, we're going to ignore things like obstructions in buildings, and we're going to say, depending on where you are on Earth, you should be able to see 1/2 of the celestial sphere if you're in a flat field, or if you're in a desert, or you're on a boat or something like that, okay? Having said that, it's time for us to go ahead and to make a model of our local sky so that I can define a few vocabulary points for you. And let me show you what we're going to do here. We're going to have a little Bob Ross time together. And we're going to attempt to make a 3-dimensional picture that looks something like this, okay? And I can show you guys how to do this. So let's start a new module. And let's call this module a 3-dimensional view of your local sky. How many of you actually grabbed a ruler? Did I ask this last time, or did I ask my 1010 class? Did any of you guys get one of these? Yeah? Mikey, no? Okay, well, Mikey, you're going to have to get creative. Find a flat thing around like the side of a book. Hey, how about calculators? Do we have calculators today? Okay, I like it. I like that very much, friends. Lionel, all right. Whew. Lionel's raising his hands in the air. That makes me happy, guys. Thank you. Okay, if you don't have a ruler, find the edge of a book or something with a straight edge to make a line here. If you do have a ruler, I recommend leaving yourself some headroom on the screen, and I recommend that we make a horizontal line somewhere in the middle of the page, maybe about, for you guys, maybe about 10 centimeters or so. Is that right for 8.5, 11? Yeah, maybe 10 centimeter line with your ruler. I'm going to make mine a bit bigger because I'm on the board here. I'll make mine 50 centimeters. Once you draw your 10 centimeter line, mark the midpoint with a dot at 5 centimeters. Now, here's a good drawing trick to draw a perfect dome, or as close as you can. Since the radius of your circle or your sky is 5 centimeters, then what you can do is you can use your ruler to mark a dot at 5 centimeters at a bunch of positions equidistant from the center of your sky here, or the center of the flat plane that you just drew in. So in my case, I'm doing 25 centimeters. So I'm making some 25 centimeter dots that are positioned at key locations. And this is so that we can just make a snazzy looking dome. A nice, neat diagram helps clarify things in your mind. A sloppy, crappy diagram can actually lead to confusion. So now I'm going to sort of connect the dots, just like Pee Wee Herman. Bam. And I've drawn myself a not too shabby looking dome of the sky. If we'd like to 3Dify this, what we can do is we can make a dash just above and below that midpoint dot. Okay. And now I'm going to connect the edges of the ground to those two dashes. And that's going to sort of help me make a disk that is the ground or the field that we are standing in. It doesn't have to be super perfect, but work on mine here. Yeah. All right, well. All right, it's not exactly my forte. Okay, so now, because I am feeling good, I'm going to sort of shade in some grass so that everyone understands that this is the ground in a field somewhere, okay? Okay. I can even put a little observer dude, an observer dude in the center of the image, okay? So just a little tiny stick figure. Probably tough to see. A key thing to do when you're making a three-dimensional picture of your local sky is to define clearly which direction north, south, east, and west are. Because I am a right-handed person, I'm going to be in the habit of putting north on the right, south on the left. That makes east into the camera eye direction, and west will be on the back side into the plane of the board, okay? And in general, unless we're doing something different, like modeling the sky's rotation, well, we can model the sky's rotation this way, but in general, you'll see me putting north on the right-hand side. Your book likes to put north on the left-hand side, so watch out for that. That can lead to some confusion. Okay, let's define a few key points on our local sky. They're vocabulary terms that I'd like to use. So first thing I want you to do is to draw a line that goes right up through the head of your observer, have it pierce the top of the sky, and we'll label it Z. This is the point directly over your head, and it's called the zenith. Next, we will define a term called the horizon. The horizon is a 360-degree ring at the base of your local sky. In other words, this oval that we drew in, that's your horizon ring. We tend to think of the horizon as a location on the ground, but for astronomy purposes, the horizon ring is actually a point on your, well, it's a location on your local sky, right? So a star will rise on your eastern horizon, move through the local sky, and set in the western horizon. And when stars are on the horizon, that means they're on that line, on that ring. Okay, there's also a vocabulary term for an arc that runs north to south and through the zenith, and that's called your meridian. The meridian is an arc that rises due north reaches through the zenith and sets due south. And I've sort of underlined the three key points on the local sky. This arc that we drew in is actually, this hemisphere is our meridian. just give you a moment to catch up. Let me show you where we're going with this. I'd like to show you a very important slide. It's a slide that tries to show you what the rotation of the nighttime sky looks like from a location on Earth that's very similar to the Rhode Island local sky. So that's 82, and this is 50. I have to remember those two numbers, 82 and 50. So let's go to 82. The rings that you see here are like, you might call them star tracks, or they call them diurnal circles. And these are the trails that stars will make as they rotate through your sky at night. Depending on what place the star is located on your celestial sphere, during the course of the night, a star will usually rise somewhere in the east. It will come up and reach its highest point in the local sky when it crosses your meridian, the meridian being the north-south line. And then it will sort of sink back down in the west while staying on these sort of parallel tracks. The angle through which the stars rotate depends upon your location on Earth, okay? From the North Pole, the stars all kind of spin around in a circle in the sky. They actually don't rise or set. From the equator, stars rise in the east and come up overhead and set in the west, sort of at a 90-degree angle to the north and south. From a location like Rhode Island, which is roughly halfway up the globe, this is sort of what the rotation of stars will look like. In fact, it's a cool cottage industry for astrophotographers to take some cool pictures of these diurnal circles. And I should have a couple of photographs of that here. Let's look at slide 84. So the camera here has been put on a tripod, and the person has taken a long exposure photograph, I don't know, maybe 5 hours or something like that. And throughout the course of the night, you can see the stars rotating somewhat around Polaris. Polaris itself is on a tiny little arc here, demonstrating that Polaris is not precisely at the north celestial pole. It's very close, but not quite there. You'll notice that some stars are so close to Polaris that they are what's called circumpolar stars. A circumpolar star never actually dips below your horizon. They don't rise or they don't set because they're located so close to Polaris. So for instance, in this photograph here, this star here is a circumpolar star, but this star here is not a circumpolar star because it sinks below your horizon. Our homework on Thursday will involve a couple of tricky questions on circumpolar stars. If you point the camera back towards the south, you can see stars rising in the east and setting on the west. They call them, star tracks or diurnal circles. People take all kinds of groovy photographs. Ooh, Caitlin, your cat just photobombed us there.
Yeah, he will do that quite often.
Okay, so lots of cool pictures of circumpolar stars exist out there on the internet. If you're an amateur photographer, if you're a photography enthusiast, you may have even messed around with that yourself. If we're located in Rhode Island, we are north of the Earth's equator, and that means we should be able to see the North Celestial Pole and Polaris in our local sky. And the North Celestial Pole and the celestial equator are the last two fundamental positions of the local sky. So where's my blue marker here? I like to put Polaris in blue. Make a line that goes from the foot of your observer and pierces the northern sky roughly halfway up, okay? And you can label this NCP. And let's put Polaris actually on the dome of the sky, okay? To draw the celestial equator in, we need a ring that runs east to west and is always 90 degrees with respect to the North Celestial Pole. So I'll take my ruler and I'll see if I can do a midpoint that's about 90 degrees, okay? And then I'm going to attempt to draw the best horseshoe that I can from the west up to the east, something like that. And let's label that CE for celestial equator. And let's put those down as fundamental positions of our local sky. Celestial pole, already defined, and celestial equator, already defined. Taken together, the zenith, the horizon, the meridian, the north celestial pole, and the celestial equator are known as the fundamental positions of your local sky. And these are vocabulary terms that we are going to use to talk intelligently to one another about the movement of stars in our sky. Okay. Having made this lovely diagram, I am now going to erase. Does anyone need another second here, or are we good?
I have a question.
Fred, take it away.
So that picture you showed of the stars, the delayed photography with the stars making those circles.
Yep.
Some circle and some like go to the horizon or past the horizon. Does that? I'm trying to understand. So every night you're going to see the same pattern, or is it change during the seasons?
Right. So in fact, it does change during the seasons. From night to night, you will see roughly the same pattern, depending on what time of night you're out there. Let's say you're out for the entire night. Let's say nighttime is 6 p.m. to 6 a.m. in a simplified world, okay? Night after night, it will be almost the same rotation. But because Earth is actually drifting a little bit around the sun, each night there'll be about a 4-minute shift, about a 1-degree shift of what stars are available in your local sky. So for instance, right now, I've been noticing that Orion is pretty close to our meridian at midnight. And that tells me that if Orion is close to my meridian at midnight, it must be rising around 6 p.m. It must be setting around 6 a.m. If you used Orion as a reference point, what you will discover is night after night, Orion is creeping more westward each night, eventually culminating at a time of year where Orion will be on the western horizon at sunrise. And then Orion will bloop, it'll be gone from your nighttime sky, and it won't come back around again until next November or so. So the times where I notice Orion are October through, March or something like that. Or maybe, I think I've got that right. It's a wintertime constellation.
Got it.
And we'll learn more about that as we go on, Fred. This can all be a lot to take in. So we're doing little pieces and modules that will stitch together into a tapestry of understanding. Let's go ahead now and let's develop some coordinates so that we can precisely describe the motion of stars through our sky. Another dimension to this, Fred, is it very much depends upon where you are on Earth, in particular, your latitude. So that makes me kind of want to define latitude and do all that stuff proper. I'm erasing. Okay, so as a little top-down structure of what I want to do, and this might take the rest of the lecture. Oh, fudge. A friend of mine wanted to join in, and I can't believe I forgot to send her the link. How do I do this? Oh, man. Oh, I know. Just a moment. Presumably, yes, there we go. The link is in my phone, and pow, that's done. Okay, let's go ahead and let's talk about what we're going to do next. We're going to be defining 3 coordinate systems that are going to help us understand the motions of the sky. So we have 3 coordinate systems. The first is going to be a review of geographical coordinates. And this is something that you probably have heard about, your latitude and your longitude. But, can't hurt to do it right, to do it again. Geographical coordinates, I've got every damn color in my pocket except for the one that I want. Okay, geographical coordinates are used to describe your position on Earth, okay? And then we're going to have two separate coordinate systems for our sky. The first is going to be called the horizon system. And the horizon system is useful for describing the position of a star on our local sky, okay? Then we have the all-important equatorial system. The equatorial system is sort of like a latitude and a longitude for the celestial sphere itself. So these are what you might call global sky coordinates that are the same for all observers on Earth. The horizon system depends upon your location. Let's not forget as well that all of these coordinate systems are angles, okay? We're used to thinking of our latitude and our longitude as a physical position on the surface of Earth, and so it's tempting to consider them to be distances, but they are angles. Note to self, don't use green anymore. Okay, let's start with geographical coordinates, something that you should be a little bit familiar with. Caitlin, can I erase or do you need a second? Looks like she's writing. This is a tea sipping opportunity for me. Okay, Caitlin, are we good to go? Thumbs up. All right. So, geographical coordinates, you've heard of it before. The two angles are called latitude and longitude. Okay, so Earth is a spinning sphere. The spin of Earth gives it some symmetry points. The axis along which it spins is unique, and that makes the equator a unique great circle that slices through Earth. A little bit of 3D geometry here. You can slice through a sphere in a variety of positions, but when you cut the sphere in half, such that you cut through the center, that is what's known as a great circle. There are many great circles that slice north to south, but the only great circle that can cut horizontally is the equator. And the equator becomes a sort of unique symmetry line for Earth, where we split Earth into a northern and southern hemisphere. So this is a good way to define our latitude. Latitude is defined as your degrees north or south of the equator. And it's customary to specify the angle and the direction, okay? We'll try a few examples in just a moment. Longitudes do not have an obvious symmetry point to start from, because longitudes are tangerine slices. They cut north to south, but the purpose of longitude is to measure east to west. Where do we begin our longitudes? One place on Earth seems to be roughly as good as another one. Well, at some point, some astronomers and some geographers got together, and they decided that a good place to begin measuring longitude from would be a line that runs through the front door of the Royal Greenwich Observatory just outside of London. And the prime meridian, as it's called, you can see here, cuts right through the front door of the observatory. A tourist could visit the prime meridian at the Royal Greenwich Observatory, and you could put 1 foot in the Western Hemisphere and 1 foot in the Eastern Hemisphere, and you could sort of take a little selfie pic there, and that might be a fun thing for you to do. In fact, at least 1 or 2 of my students have gone to Greenwich to see the prime meridian after this class, And one of them even brought me back my very own prime Meridian pencil from the gift shop. That is a treasured item on my rolling cart at CCRI. So please think of me when you visit the Prime Meridian gift shop, okay? We're going to measure our longitude as degrees east or west from the Prime Meridian. So let's do that. It's the degrees east or west from the Prime Meridian. Now, a couple of useful examples that might be helpful during our homework session this week, okay? Let's take our own fair city of Providence, Rhode Island, where I am lecturing from. We have a latitude that is roughly 42 degrees north and a longitude which is roughly 71 degrees west of the Prime Meridian. In fact, if you guys have a compass app on your iPhones, and I think Google phones have the same thing, you'll discover that we actually have a very high precision measurement of our latitude and longitudes right here in our pockets. If I go to my compass app on the iPhone, I have things focused at a distance, and you saw what trouble I had, so I don't want to start tinkering with that. But right here, oops, on my compass app, I actually have a measurement of my position on Earth, not only specifying 42 degrees north or 71 degrees west, but actually, what do we see of those secondary angles there? I actually have my position down to the arc minute and even arc second accuracy, right? So if you guys want to take a peek here, my exact coordinates here are 41 degrees north, 49 minutes of arc, and 23 arc seconds north. And for a longitude, I have 71 degrees, 24 minutes of arc, and 44 arc seconds west. Now, I was thinking if someone was in the class here and someone was, located in South County or somewhere far away. Yeah, Caitlin, where are you at? Wait, you're muted.
I'm all the way in Charleston.
Okay, cool. So let's take a peek. Let's find out. Let's see if we can measure a little difference here in our coordinates.
Yeah, I have mine. For the exact one, my latitude is 41 degrees,
Yep.
26 arc minutes, and then 51 arc seconds. And then my longitude is 71 degrees, 39 arc minutes, and 11 arc seconds.
Okay. And did you say 26 minutes of arc?
Yes,
Okay, cool. So, and I'm sorry, was it Charlestown? Is that what you're at?
Charlestown, yeah.
So from Providence to Charlestown, you can see there's, a roughly, 25 arc minute difference between Caitlin and I, right? So whereas, it seems to be that Rhode Island spans about 1 degree or like maybe a half a degree of latitude, but we can actually use these high precision measurements to calculate the distance between us. Now, of course, knowing the radius of Earth, we could use the small angle formula to convert this into a number of kilometers. I'm somewhat tempted to do that as an in-class exercise, but I could easily go off on a flight of fancy and not get to equatorial coordinates, and then I will feel bad, okay? Let's try one more example just for fun. And this is great. Thanks for contributing there, Caitlin. Could we handle describing the latitude and longitude of the North Pole? Let's see what that goes like.
I have a quick question.
Yeah, sure.
My mic wasn't working before when you were erasing the top. I didn't get 2 and 3 for the coordinate systems.
Well, you're going to get them in a moment because that was almost like a little bit of top-down structure of what we're going to do here. So the first was geographical coordinates. The second was the horizon system. And the third one was the equatorial system. But I think it's okay that, who is talking to me? Is that Paige or?
Yeah.
Oh, hi, Paige. Paige, it's not a big issue because in a second, I'm going to erase this and do number 2 horizon system. So
okay.
That was almost like an unnecessary luxury of showing you where I was going. You know what I mean?
Yeah. Okay.
All right.
Thank you.
Not critical. All right. But let's try this. Let's see if we can figure out the latitude and longitude of the North Pole just using our noodle. Okay. So latitude shouldn't be too hard. Anyone handle that? We want a picture to help here. Here's our prime meridian. Okay. So what should the latitude of the North Pole be? Anyone? You know, it's one thing to listen to me yap away. It's a totally different thing to use that knowledge. It's always more challenging, right? Come on, someone can do it. I know if you try hard.
Would it be at 0?
So remember, we define our latitude as degrees north or south of the equator. So 0 would actually be on the equator, right?
Oh, right. So I thought we were defining longitude.
360? Oh, no, half of that, 180?
180 is half of a circle, right? But are we going half of a circle, or you know what? This might be a good time to use. Oh, I got to use all my goofy Zoom tools here. Share screen.
90.
Yeah, right. Because if you, how do I do this here? Okay, so if this is Earth, right? And this is just, you know, some basic geometry stuff. If this is the equator, and that's 0 degrees, we are, and here's the North Pole, right? We're not going half a circle, we're going a quarter of a circle. Capiche?
Yeah,
Okay, you guys got it now, right? So, but a latitude requires an angle plus a direction. 90 degrees. Talk to me, people.
North.
That's right, okay. How about the longitude? How about the longitude of the North Pole?
I want to say it, but I'll be wrong. Do you mind?
Well,
I think I got it though. I'm
the
confident.
time where they let me cut your fingers off for wrong answers, so I guess the consequences aren't that steep, you know.
Okay. I will say it's undefined.
That's right. Okay, so Lionel knows some things. I like this. You're no fun. All right. If you take a close look here at the diagram, every line of longitude actually runs through the North Pole. So this coordinate is actually what we call in mathematics degenerate. Okay, it's a degenerate point. And that's okay that it's degenerate. Probably a less dorky way to say that is just to say it's undefined. It's undefined because every line of longitude runs through the North Pole. However, that does not break the system, because unlike 42 degrees north latitude, which could be referring to Providence, Rhode Island, or Osaka, Japan, or something like that, 90 degrees north is a unique point. And this is actually, there's a thing in this like higher order topography of mathematics that if you create a coordinate system on a curved surface, there will always be 2 points that are degenerate or multi-valued, right? And in this case, it's okay because 90 degrees north is a unique place. You could only be one place on Earth if your latitude is 90 degrees north. All right, this is stuff that probably you heard about at some point in your life, but it doesn't hurt to review it. We need to know where we are on Earth because that's going to affect how the stars rotate through our sky. Let's start talking about stellar coordinate systems. May I erase, students? Any objectors here? All right.
You had an objector on the chat.
Oh, geez, Mikey. It's hard if I can't hear you guys, okay? So, Mikey, you're screwed. Can you just go back and watch the recording on YouTube, or can someone take a photograph? I know you guys can like get in cahoots with each other on the chat thing here. Okay, you know, oh, Mikey doesn't object. Oh, I see, okay. All right, so he was not an objector. He was a conscientious objector. Let's go ahead and let's define the horizon system. So Paige, this is the number 2 that you missed earlier, okay? The horizon system is a coordinate system that we use for the local sky. And that means it's great when you're out with your buddy or at your grandma, if you're at a telescope together, say like the Margaret Jacobi Observatory. And it's a simple coordinate system to help you track the position of a star. The two angles are altitude and azimuth. Okay, so we define altitude as the degrees of a star above the, and I'm going to put this in parentheses, degrees of your object above the nearest horizon. In other words, it's the degrees up of a star from the ground. Let's underline above. Your azimuth, which is kind of similar to direction, north, south, east, west, azimuth is measured in degrees along the horizon, measured clockwise from north. So it's nice to be able to practice this when we're in a classroom together, but since we can't do that, let's grab a 3D local sky here. In fact, let's go back to that lovely picture that we made together earlier. And Rachel, I'm so glad that you could join us today. I forgot to send you the link until about halfway through the lecture. So Lisa, yeah, and my friend Rachel's here to hang out and learn some astronomy with us. She's a good friend of mine and also a talented engineer and a scientist herself. So it's always nice to have some pals coming into the lecture show. Let's go ahead and let's put a fake star. Let's put a, I don't know, let's put a blue star somewhere on our sky, okay? And it's, you know, a little difficult with the 3D perspective here, but let's pretend this star is somewhere over in our northwestern sky, okay? So what I would do to define its altitude and its azimuth is I would first, so here's north, right? I would first kind of swivel along my horizon until I got to the closest point on the horizon. To get my altitude, I would simply measure my degrees up from the horizon. So if I can make a sort of angle that looks like so, I would say that this star is maybe, I don't know, 60 degrees above my northwestern horizon. It looks like 60 degrees to me because it looks like it's more than halfway up the sky. So its altitude is this angle here, just degrees up from the horizon line. To measure the azimuth, we start north. Let's use red for this, I guess. We start north. We swivel clockwise around the horizon ring until we get to the closest point. And that angle there is, let's see if I can do that. That angle there is our azimuth. Anyone have the guts to estimate that azimuth angle for me? See if you can do something with this knowledge.
Like 250?
So more than 250, right? Because let's go back to our unit circle. Remember that math class stuff? So 0 degrees, 90 degrees, 180 degrees, 270. So that's why I'm thinking it's got to be greater than 250. Whoever that was, I don't know who that was.
Should be like 290-ish.
Yeah, 290, 300, something like that, okay? In fact, for a couple of cheap examples, azimuth is very much like direction. Each direction on the horizon has a unique azimuth associated with it. So for instance, the azimuth of due north, once again, is 0 degrees. Due east is 90 degrees. Due south, 180 degrees. And this is in case you forgot your basic geometry. Due west is 270 degrees, okay? And that all just falls under the heading of azimuth, okay? That's not altitude. Let me show you how this works in practice, okay? Telescopes basically come in one of two different designs in terms of the the pier or the tripod that's used to point at stars. And let me show you guys a telescope that really just gives me the willies when I fantasize late at night, okay? I'd like to introduce you to the plane wave 1 meter telescope. And it's here seen on an altitude azimuth mount. Now, it's not too expensive. So if you have any rich aunts or uncles that want to donate to the Margaret Jacobi Observatory, I've got a few ideas in mind, okay? Think about buying this for your professor for a Christmas present. And this is a serious research grade instrument, right? It's got a dual Naismith port, so you can attach a CCD camera and a spectrograph. Here's a video of this thing slewing in the clean room. And I want you guys to watch this thing in action here. So this telescope is on an altitude azimuth mount. So you can see the technician is swiveling here, both in azimuth, it's rotating around the sky, and you can see those fork arms there hold the telescope tube so it can be lifted up and down in altitude to point towards a star. A modern day telescope like this has a computer system with a model of the rotating sky, and it will track stars as they move through your local sky quite effectively. Without that computer, if you had to do this by hand, it would be a very annoying process. And the reason why is because although altitude and azimuth are simple and make sense from a sort of human-based perspective, remember that the picture I showed you earlier of our rotating nighttime sky, what was that, 82? Yeah, from a Rhode Island local sky, a single star throughout the course of the night will change in both altitude and azimuth in a complex way over the course of the night. It will rise in the east at 0 degrees altitude. And from a Rhode Island perspective, it will come up on this kind of stellar track that pokes into your southern sky. And every moment of the night as a star rotates, it's drifting both in altitude and in azimuth in a complicated way. However, a modern computer can keep up with this. That's fine. What makes the horizon system, what makes the horizon system or altitude and azimuth so simple is you can go out to the telescope with your Grammy and you can say, Grammy, I need you to point the telescope at the Orion Nebula. And you know your Grammy's going to be like, well, I don't know where the Orion Nebula is. And you say, that's simple, Grammy. I need you to just point the telescope, due west in azimuth, and I want you to go up to an altitude of 30 degrees and pow. There the Orion Nebula is, at least for a few moments. However, what if you need to call your Grammy up in Pensacola, Florida? And you say, Grammy, get on the horn here. I need you to go out to the plane wave 1 meter, and I need you to put the Orion Nebula onto the telescope and collect some data. If your Grammy says, I don't know where the Orion Nebula is, you can say, well, in Rhode Island, it's 30 degrees altitude. But hold on a second. If it's 30 degrees altitude for a Rhode Island observer, I don't think it's going to be 30 degrees for a observer in Florida or somewhere else in the earth. And that's the problem, right? Because if you and your Grammy discover a nebula and you want to call it Grammy's Nebula, then you need to let all the other astronomers know that they cannot name that nebula because that's named after your dear old Grammy. And what we need then is we need another coordinate system that will actually stay fixed to the sky so that when we make these cool new discoveries, other people will be able to find them and recognize them from any location on Earth. And so the horizon system is useful for pointing your telescope when you're both in the same location. We also need another set of coordinates, a kind of global sky coordinate, where stars will have a fixed position. In other words, we need latitude and longitude for the sky. But here's where things are going to get a little tricky and a little interesting, okay? So our third coordinate system is called the equatorial system. And let me just keep track of time here because I'm usually not good at that. Oh yeah, I'm actually doing good for once. All right. Let's start by getting a few things clear before I launch into number 3, the equatorial system. A few simple things that you might not have thought about before. And here's the first one. A spinning Earth takes 24 hours approximately to spin on its axis. It's actually 2356, but let's not talk about that. Okay. Anyways, let's lie and let's tell you that it's a 24-hour axis spin. And in 24 hours, the Earth and therefore the sky will rotate through a 360-degree ring. If you divide 360 degrees by 24 hours, you get a magical number. Go ahead and punch that into your Casio FX260 Solar. Tell them what you get.
15.
Exactly, and watch the units here. 15 degrees per hour. That is not a random coinkydink. The Babylonians designed the hour that way. The hour was consciously designed to be a 15-degree wedge of the sky. Of course, Babylonians are obsessed with sexagesimal number systems, which is why we have minutes and seconds and arc minutes today. This means for astronomers, there is a weird sounding conversion factor that doesn't make sense to anyone except for an astronomer, and it goes a little something like this. 15 degrees is equal to 1 hour of sky rotation. And you might discover in our problem sets this week that this is a useful conversion factor. 15 degrees is equal to 1 hour. Extremely important. This means that at least in terms of celestial longitude, while I could measure celestial longitude, or what we're going to call right ascension, I could measure it in degrees like I did normal longitude, but it's going to turn out to be way more useful in practice to measure that coordinate in hours and minutes, which is going to take a little getting used to. It's horrible to learn, but extremely practical and useful once you're out at a telescope and you're doing stuff, okay? The sky is perpetually in motion, and it makes better sense to measure one of these coordinates in time. Okay, so that's the first order of business. Here's the second order of business. In our last class, according to Caitlin, at the beginning of our lecture, we had a lecture on Earth's orbit and a couple of basic vocabulary terms. And we also defined 4 key points in Earth's orbit: the spring equinox, the summer solstice. Hold on, let me get out of this stupid thing here. Let's get to my slideshow. In our previous lectures, we learned about this very important vocabulary term called the ecliptic. And here, I'd like you guys to take a look at this slide, slide 51. And just to help memorize things, why doesn't someone out in the studio audience regurgitate the second definition of the ecliptic? That's the ecliptic definition number 2. And I already know that you forgot this. That's why I want us to read it out loud. Someone want to do that for me? Yeah, Paige, I'd like to hear it.
I don't know if this is right or not, but zodiac.
Well, functionally, the ecliptic definition number 2 is the zodiac. So it's not that you're wrong. It's just I wanted the definition number 2 of the ecliptic. I think that would be useful for us all to hear again.
It's the yearly path of the sun against the background stars.
That's right. So if we watch the sun very carefully night after night, and honestly here a slightly different picture. Oh man, it's the next slide. I'm so good. I thought ahead for myself. Okay. If you could carefully jot down the position of the sun relative to the background stars, night after night, day after day, however you want to look at it, the sun is drifting eastward along the path of the ecliptic. Our original definition for the ecliptic was something much simpler. So that was 52. Let me go to, I don't know, 34, something like that, somewhere around here. Our original idea about the ecliptic is that the ecliptic was the path of Earth around the sun. It's quasi-circular orbit. That's great. That's a good definition for the ecliptic. But if you are in an Earth-based reference frame, if you're looking at the sky from Earth, then night after night, slide 52, please. Okay, night after night, the sun is kind of drifting by about 1 degree along this path relative to the background stars. And yes, Paige, those are the constellations of the zodiac. That's why people worship them, because deep down inside, they're all just little sun worshipers. You know, they just can't get over this one star that happens to be closest to us. And if you track that star, you can see it drifting, and that path is also called the ecliptic. But that opens up a bunch of cool ideas, right? Because if the ecliptic is also the path of the sun against the background stars, then those 4 key days of the year, the spring equinox, the summer solstice, the fall equinox, those are not just days of the year, they're also points on our sky. For instance, the spring equinox, which is the point on the sky where the celestial equator and the ecliptic intersect, this is a point on your celestial sphere. And guess what? This point actually rises and sets every day, just like a star. And I have a slide for that as well. Let's find this here. Okay, I'm trying to tell you something that's actually pretty confusing here. So just bear with me for a second. The spring equinox, in fact, we're going to take this as a note. The spring equinox is 4 things at once. Where are we here? The spring equinox is 4 things all at the same time. The spring equinox, first and foremost, is a point in Earth's orbit. That's how we originally considered it. Fine. Number 2, it is also a day of the year. Which is approximately or roughly March 21st. And I can't remember if I told you guys this or the solar system class this, but because of leap years, because there's not exactly an equal number of days of the year, the spring equinox will drift by about a day each year. It'll be the 20th, the 21st, the 22nd, the 23rd, and then leap years help to reset that. It actually drifts in a slightly more complicated way, and sometimes it can even be on the 19th. Hell, did we talk about this before? What's the spring equinox this year for 2022?
Yeah, we did talk about this. I think it's the 22nd, and it's actually the 22nd until like 2025 or something like that.
Yeah, in one of these classes, I was kind of cycling through 2022. Timekeeping, oh, sorry. It's Sunday, March 20th this year is the spring equinox, okay? Okay, so the spring equinox is a point in Earth's orbit. It's a day of the year. It's also a point on the sky. No kidding. You've never noticed it before because, well, there's nothing there, or most of the time there's nothing there. The spring equinox is a point on the sky somewhere just below the constellation of Pisces, and each day this point rises in the east and it sets in the west, just like any old planet or star. You don't notice it because there's usually nothing there, except one day each year, a special astronomical object appears at the spring equinox. Once a year, there's a special astronomical object that will appear at your spring equinox. Anyone out there think they can guess what it might be?
Is that the comet?
It's not a comet. It's a special astronomical object that only appears at the spring equinox once every year. It's the fucking sun, okay? That's where the sun is going to be on March 21st, okay? And by the way, you know where the sun's going to be on, where are we here? On June 21st, it's going to be up here in the foot of Gemini. And on September 21st, the sun will be located in Virgo here. And on December 21st, the sun will be here in Sagittarius. That's the significance of those 4 points. It tells us where the sun is on key days of the year. Okay, so if that wasn't enough, not only is the spring equinox a point in Earth's orbit, a day of the year, a point in the sky, but the spring equinox is also a moment in time. And this is because during the course of a single day, Earth never stops drifting in its orbit. Now, this might be a little easier to explain through the camera lens if we focus instead on the summer solstice, which you'll remember the summer solstice is that day of the year when Earth's axis tilt, its 23.5 degree axis tilt, the North Pole is tilted most directly towards the sun, which is in this diagram is you. You're the sun's eye, the camera eye, okay? A day before the spring equinox, there is not a perfect alignment between the axis tilt and the sun. A day after, there's not a perfect alignment. But then you start scratching your noodle and you start thinking about this and you say, wait a minute, on March 21st, it's not like Earth hovers in space frozen. It's during the course of a day, it's doing a very slow 1 degree drift along the path of the ecliptic. And that means while we approximate the spring equinox as a day, the actual spring equinox is a nanosecond, a peak, an attosecond in time when the Earth's North Pole is pointed most directly towards the sun. And if you look at Google over here, you'll see, where are you, baby? That the actual moment in time will be 11:32 a.m. Sunday, March 20th, this year. This can lead to hideously confusing questions on an astronomy midterm exam. Questions that sound like, describe the location of the spring equinox at noon on the spring equinox. Ooh, boy, I hope that a question like that wouldn't appear on the test. I wouldn't do that to you. Oh. Okay, all right. Anyways, the spring equinox is a reference point that for our coordinate system, we're going to use to measure celestial latitude and longitude. So now that you've had the appropriate background shenanigans, let me introduce to you a coordinate system that we will use for our lab today to find some of the brightest stars in the sky. Okay. Number 3, the Equatorial System. Which is a set of coordinates for the global sky. And this should be new to, unlike latitude and longitude, this should be pretty new to you guys. So the 2 angles we use are called declination, or astronomers represent it as dec. Sometimes they use a delta for declination too. So declination, and the other coordinate is right ascension, or RA. So astronomers, when they talk to each other, will say, what's the RA and dec of that star galaxy, okay? Now, declination is the coordinate that's kind of like latitude, very much like latitude, actually. Right ascension is the coordinate that's very much like longitude. And the declination is going to be defined exactly like latitude from the celestial equator, but we don't use north and south. By convention, we use positive or negative. So we could define it simply as the degrees of a star or a doodad, the degrees positive or negative from the celestial equator. All right, easy peasy pie. Right ascension. We cannot use the prime meridian as a measurement reference for right ascension. And if you look at my globe here, you can quickly figure out why. I'm going to take my horizon ring. I'm going to line it up with Greenwich, England, where the prime meridian is. And over the course of a 24-hour day, the prime meridian will be rotating and will be sweeping through lines of celestial longitude. We need to pick a reference point on the globe that is stuck to the globe, not connected to a rotating Earth. And the powers that be decided that the most useful reference point, rather than being any one particular star, would be the spring equinox itself, where here I am invoking the spring equinox as a point on the sky. This is going to be the equivalent of the prime meridian. It's going to be the 0 point for right ascension. We will not measure east and west, and we will not measure in degrees. We're going to measure in hours and minutes, which is a little goofy your first time around. So the right ascension could be defined as the hours and minutes of a star measured eastward from the spring equinox. Okay, students, here I need help remembering what the hell eastward means in space. What's eastward mean in space?
Counterclockwise.
Very good. Excellent. Counterclockwise, and counterclockwise as seen from north, okay? Because if you look south, then it becomes clockwise. It's a little confusing. Because it will help us in our lab today, we should practice by trying to see if we can think our way through what the right ascension and declination of a number of different points in the celestial sphere would be. By practicing it, that's how we'll really get to understand it. Let me just take a moment here to make sure you guys have got all that down. And I think we have just enough time. We have just enough time for a little 3-minute practice problem. After that, we'll take a little pause for 5 minutes, and then we will do our lab where we find some stars using these coordinates on the celestial sphere. Okay, may I erase, students? Any objections here? Okay, there we go. Okay, if the 4 key points are points on the celestial sphere, and here, notice that this diagram of Earth is tilted. It's tilted 23.5 degrees so that the ecliptic is actually horizontal here, okay? The spring equinox, the summer solstice, the fall equinox, and the winter solstice are all fixed points on our celestial sphere. And that means they should have fixed coordinates on our celestial sphere. And knowing the definitions of those coordinates, we should be able to think our way through what they are. So let's do this as an example problem, okay? And this is actually going to be helpful in a whole number of different places. So in class question, find the right ascension and declination of the 4 key points on the celestial sphere. We'll start with the spring equinox. This will be a little awkward to get started on. We need a right ascension and we need a declination. People usually label the coordinates RA first and declination second. Does anyone want to be a brave soul and, you know, see if they can, you could give me both, or you could try to give me one of those coordinates. Let me see here. So I'm looking for this point right here. What's the right ascension and declination of that point? Anyone think they could?
Would the right ascension for the spring equinox just be the point in time in which it's at?
Okay, no, I see how you're asking that question. David, even though we measure right ascension in hours and minutes, right ascension is not time. And I want to disabuse you of that idea. Right ascension is a coordinate measured in hours and minutes. And your first time learning it, it's so tempting to think of it as time, but it is not time. It actually has a relationship to time, but don't do that yet, okay? It's just a coordinate, a position on the globe that happens to be measured in hours. Why don't, David, instead, you read me the definition of right ascension?
So it's the hours and minutes of a star, or whatever we're measuring, eastward counterclockwise from the spring equinox.
Correct. In other words, you start here and then you measure usually along the celestial equator, but just like longitude, like right ascension, lines of constant right ascension are like these tangerine slices, right? So you can measure actually the entire tangerine slice around. But for convenience, for starters, let's just move along the celestial equator. So you start here and you measure counterclockwise from north, all right? So if you're measuring from the spring equinox, what should the right ascension of the spring equinox be? David, anyone? Anyone understand? No, it's really tough to kind of jumpstart this car, but that's why we have to try, okay?
24 hours.
Huh, well, Who was that? Caleb? Was that Caleb's voice I heard there?
Yeah.
I'd recognize your voice anywhere. Caleb, you're not wrong. You're just weird. That's all. I just want you to know that you're different, okay? But 24 hours in a way is correct, but no astronomer would do 24 hours. They would just call that 0 hours, right? But in a sense, 24 hours is also correct. But let's do it this way. We always list right ascensions in a kind of military time format. 00, 0, 0. That's better than 24 hours because it resets. Okay, anyone want to try the declination based on the definition? Someone read me that definition, please. Just regurgitate that right off the page. Caitlin, are you talking to me? You're muted.
Sorry. I always think I click it, but I don't. Declination is the degrees positive or negative from the celestial equator.
Okay. So what should the declination of the spring equinox be? Noticing that the spring equinox is on the celestial equator, here shown in red.
Would that be 0
Yeah.
0 degrees.
degrees?
All right, there we go. Let's try another one. This time, let's try the summer solstice. This isn't easy your first time around. That's why we're doing it, okay? So right ascension and declination. Anyone think they're starting to get the swing of the thing here? Give me the RA or the dec of this point here.
Would the declination be plus 23.5 degrees?
Damn, you're good. Excellent. And I like that you actually specified the positive too. That warms the cockles of my heart. Okay. Positive 23.5 degrees. And you can see that right from the diagram. What do they say in the textbooks? By inspection. That's what they say, by inspection. Okay. Nice job, Caitlin. How about the right ascension? Try to give you a little hint here, okay? So
6 hours.
very good. 6 hours. If you go all the way around the sphere, it's a 24-hour rotation. So the summer solstice is a quarter turn, making it 6 hours. Okay. Let's try the fall equinox. I need an RA and I need a dec.
So if the RA is another quarter turn, it would be 1200 hours. Sorry, that's military time speak.
Yep, that's okay. We can do 1200 hours. I like it. 12 hours. How about the declination? This is always a moment in this class where some people start to get it and some people start to get scared. If you're scared, don't worry. It just takes a few extra minutes to click, and it will if you try. What's
That'd
our...
be 0 degrees again.
Yeah, that'd be 0.
Yep, 0 degrees, okay? And then last, we're going to try the winter solstice. I think today's lab will help with this too, because we'll be using these coordinates to look up some stars. How about the winter solstice?
Would that be 18 hours?
Very
for the
good.
RA?
Yeah, because we start at the spring equinox. We're going 3/4 of the way around in tangerine slices. So that's 18 hours right ascension. How about the declination?
It would be minus 23.5 degrees.
Excellent.
Yeah.
All right. You
So it
guys,
wasn't too difficult.
you guys are doing better than the average bear. I like it. So this is just an example. Now, in practice, if we go look at a fun star, like, I don't know, I love the star Betelgeuse, of course, famous red giant. We had this in our, we had to calculate its diameter for our homework on Thursday. And we learned that it was 9 AU in radius, right? Notice if you look up any star on Wikipedia, they will usually, actually always, give you its coordinate position in equatorial coordinates right there. in the highlighted area. So you can see that Betelgeuse has a right ascension of 5 hours, 55 minutes. Check out the precision on this bad boy. They've estimated its position down to, what is this, like a millionth of an arc second or something, or 100,000th of an arc second. So 10.30536 seconds of arc. The declination, positive 7 degrees, 24 minutes of arc, 25 arc seconds and change. You know, when you measure the positional resolution of a star to this level of precision, you can actually start to detect what's called its proper motion. And for some stars, for nearby ones, over many years, you can actually measure a small drift in their coordinate position due to the fact that all of these stars are actually drifting around the Milky Way galaxy. Usually they're so far away that they barely change except over long time scales. But if you can measure their position to increasingly more sophisticated accuracies or precisions, you can then you can sort of measure its motion along the sky. Very cool. Okay, this concludes our lecture for the day, and we are going to do a short but fun lab on the finding some famous stars in the celestial sphere. Rachel, if that's of interest to you, stick around and hang. If you got to do stuff, that's cool too.
I could probably grab the first exercise.
Okay, yeah.
I want to see how this works, you know, and for real things. So
yeah, and that's part of the fun. Of course, it's really cool when everyone can kind of have their own, or a couple of people can each have a globe and kind of futz around together. I really love this lab when we're doing it in person, so I feel sad about that. But, you know, pandemic is real. We're all muscling through it, and I'll use my remote camera phone and we'll do it together. That'll at least make it fast. That will be its virtue. Okay, so do you guys want that little 5-minute iced tea break that we like to do? Does that work for everyone? Okay, so let's see. iPhone time. I'm probably drifting here. It's 1:08. So let's say you know, a little before 1:20, maybe 1:18. We'll crack to it. Okay, that'll give me a little iced tea break. All right, I'm going to pause. Do not let me forget to unpause this recording, okay? I'll see you guys in 10 minutes. Okay, students, welcome to our second laboratory exercise on celestial spheres. As I was about to mention to the class, there is a celestial spheres handout under your lab number 2, but we only need to print the first 2 pages. The other part of the lab is actually really fun and sophisticated, but I think it'll just take up a little too much time and you guys will start to lose it on me. But I've got a couple ideas to go off-roading here, including at the end of our little short lab, a little astrological divination reading, okay? So replete with astrological readings. Those of you who do not have a printer, okay, fine, but I want you to take pencil and ruler, and you don't have to reproduce the text, but I want you to reproduce the boxes that you see in table 1, table 2, and table 3, none of which take a very long time. This is a short and relatively fun, easy lab. We're going to do an extra little bit in that space there too. So if you can reproduce tables 1, 2, and 3, great. Otherwise, print it out and write along with me. Oh, now I remember what I need. I need my remote camera phone, which hopefully is sufficiently charged. Just a moment. Let's see here if we can connect. And we are going to go share screen to our iPhone. A plug-in, what the shite? It should be plugged in. Okay, Zoom like constantly makes you reinstall things. Whatever their latest version of spyware is that they're using to track me. Okay, there we go. We're connecting to our remote camera. Aha. And boom. We are ready to lab, okay? I'm going to use my high-tech camera holder, okay? And let's start our labs in the usual way. Please put your name down so that I know who you are. Don't forget, I always need to know your section. I have over 100 students or close to 100 students. So every time you submit something, every time you write something, astronomy 1020, and then don't forget to put your section. Daytime students are 001, night students are 102, and the distance learning people, the remote class, who I'm allowing to tag along here, your section 600. So write down whichever section you are. Another great idea for bookkeeping, right underneath it, lab number 2. This will remind you what you should be submitting it under, and it will help you keep track of what you've submitted over the semester. I've learned this the hard way. This is a smart thing to do, okay? Okay, what you can see in table 1 is you can see the equatorial coordinates, right ascension and declination, of the 10 brightest stars in the sky. These are the 10 most famous stars in our sky, or of the most famous. Our job is to use the coordinates, find them on the celestial sphere, and then identify the name of the star and the constellation in which it's located. Actually, we have to do a little bit of foreground here. I knew there was something I was forgetting. A quick word about constellations. Does anyone remember from our first lecture how many constellations are on the celestial sphere or on the nighttime sky?
88.
88.
Yeah, you guys are impressing me. I like it. You know stuff. Okay, so that's right. 88 constellations on the celestial sphere. But get this. The constellations are more than just simple stick figures in the sky. Constellations represent areas or territories on the sky. And if a star or an interesting galaxy was located here, you'll notice that astronomers have drawn this boundary in space around the constellation of Orion, so that anything within this territory or zone is part of the constellation of Orion. Just like if you threw a dart at a map of the United States, you would have to be in one of the 50 states of the US. If you threw a dart at the celestial sphere, you're always going to be in one of those 88 constellations recognized by the International Astronomical Union. And just like states in America, the boundaries of the states are somewhat crazy because they follow around the little stick figures. So I want us to orient ourselves on the celestial sphere here. Let's pray to Jeebus that I can reconnect to the iPhone because this thing gets cranky. Okay, let's see if we can do this. Boom, boom. Yes. Oh, come on, baby. Yes, it's a good Zoom day. Okay. Hopefully there's enough light here for us to see. So if you look at my celestial sphere here, you can see stars located here as these kind of yellowish disks. They've represented the brightness of the star by the size of the disk, as if you were exposing photographic film. The names of the stars are in black. The stick figures are the solid blue lines. The names of the constellations are shown here in blue. And if you guys can see these dotted blue lines, those are the boundaries to the constellations. That matters because during the course of this lab, we're going to be asked to identify in what constellation is this star or planet, and we have to make sure we don't cross the dotted blue lines, okay? So let's also just kind of orient ourselves here for the labels. On my globe, you guys can see that the celestial equator, let me use my horizon ring here. Okay. The celestial equator, the projection of Earth's equator, is this seam that you see along the globe here. What is the declination of the celestial equator? This thing is expensive and out of print, so I don't want to break it. What is the declination of the celestial equator, friends?
0, correct?
That's right. It's like latitude. This is 0 degrees dec. And you can see as I measure declinations, each horizontal line here is going to be plus or minus 10 degrees declination. So positive 10, positive 20, positive 30. Hey, by the way, is anyone curious about why everything is written backwards here? Because the sky is curved, I should have an index card here somewhere. Okay. I think the idea is that you're supposed to like look through the globe and you can read the names of the constellations with a baffle here. I prefer this to use my good old fashioned dyslexia and read it backwards. So we can see what works for you guys. Okay. Let's see. Positive 10 dec, positive 20, positive 30, positive 40, 50, all the way up to Polaris, which is roughly at positive 90 degrees declination. Now, you'll notice that we can also see the hours of right ascension labeled on these tangerine slices. 0 hours of right ascension. This is a bit busy here, but there's 1 hour of right ascension, 2 hours of right ascension, 3 hours of right ascension. Now, they've kind of given us these intricate tick marks that they have put at the positive 10 degree declination mark. The big tick marks are each 20 minutes of right ascension. The little hashtags are each 4 minutes of right ascension. So why don't we get into it and let's see if we can find a star. The first star of interest is at a right ascension of 6 hours and 43 minutes and negative 17 degrees dec. So what I'm going to do is I'm going to rotate my globe here, until I get to 6 hours of right ascension. Does this look okay on your screens, guys? You can see this pretty good? Okay. So here's 6 hours of right ascension. There's 7, and we at 6:43. So let's count 6:20, 6:40, and that tick mark is 6:44. But remember, 6 hours and 44 minutes is a tangerine slice going up and down. So I'm going to kind of drag down to the celestial equator. That's where I want to start measuring my declinations from. I think that's about good, somewhere around there. Okay. And what's our declination again?
Negative 17.
All right, so we're going to go down minus 10, minus 20, and back a little bit. What is our star?
Sirius.
Sirius, the dog star. And the constellation?
Canis Major.
Canis Major, the big dog. Okay, so let's get that down. So we have Sirius, the dog star. Sirius, of course, is the brightest star in the sky. We'll learn a lot about that over the course of this semester. Canis Major, the big dog. Okay, next up, 7:37, positive 5. Let's see if we can increase our speed a bit. 7 hours and 20, 7 hours 40, back 4 minutes is 7:36, right? That's pretty close. Start at the celestial equator and we go up positive 5. Boom. What's our star?
Bro. I can't pronounce it. Jeez.
Procyon.
Procyon.
And that's in Canis Minor, the little dog. Ooh, here we go. Oh, that's not
What was the constellation for the first star? I missed it.
Yeah, sure. Let me get my high-tech holder in action here. The first constellation was Canis Major. So now we have Procyon in Canis Minor. Now listen, guys, if you want to see these stars tonight, I don't know if it's clear tonight, but I've been keeping track of these because Canis Major and Canis Minor are the two dogs that follow at the heels of Orion. And right now, Orion's been up in our sky pretty close to the meridian around midnight. I've been noticing it when I walk back and forth to my studio. And Sirius and Procyon are very bright stars, and they follow on the heels of Orion. Now, keep in mind, this globe is all backwards right now. So normally when you see Orion, it's actually, I could flip this around. Orion is facing the other way, and you will see Sirius down below and Procyon kind of up above. These two dogs are kind of following. Oh, here we go. Let's see here. These two dogs are kind of following at the heels of Orion. So if you go out tonight, you should be able to find Orion pretty easily. I challenge you as part of your amateur astronomer development, see if you can find Sirius, the dog star. It'll be super freaking bright. And also see if you can find Procyon. That's some next level cool shit, okay? Find Sirius and Procyon trailing behind at the heels of Orion as he hunts across the wintertime sky. That's some sort of aspirational observing for you there, okay? Next up, we have 20 hours, 40 minutes, and positive 45 degrees. So we will carefully rotate over to 20 hours. Just a moment here. Let me get my grease pencil. Okay, so 20 hours and 40 minutes. That's pretty easy. We can just follow that down. And then positive 45. So we got to go up positive 10, positive 20, positive 30, positive 40. And we have arrived at
Deneb.
Deneb in Cygnus the Swan, another legendary bright star in our sky, seen all throughout the summertime. Deneb's pretty high up, so you can actually see it almost throughout the entire year. Hold on, let me get my zoom back. So I like seeing what you're seeing. Shoot, escape. I want to get back to that window where I could. There we go. Okay, Deneb, and that was in Cygnus the Swan. (1948) positive 9 should be pretty close, right? So here's 19 hours. Here's 20 hours. And 1948, let's see, 44, 48, positive 9 brings us up all the way to this mark. Altair is the eye of the eagle. Aquila is the eagle. So we're at Altair, at Aquila, the eagle. Deneb and Altair make up something called the summer triangle, a really big 90-degree triangle that splashed across the sky, 3 very famous stars. At some point, I'd like to invite you guys to come out to the observatory. For the nighttime students, I'll take you out as part of the class, but the rest of you can come on a Wednesday, or if you want to piggyback on the night classes journey. It's really fun once you know some stuff to kind of go out and look at this stuff with your own eyes at the telescope. You'll have a blast. All right, 513 positive 46 is number 5. So let's rotate back around to 5 hours, and 13 minutes will be 4, 8, 12. So somewhere around there. And then we're at positive 46, 10, 20, 30, 40, 46. Capella is the eye of the goat who rides on the back of Auriga, the herdsman. It kind of looks like a big square circle, or like a lock, like old-fashioned key and lock. That's what it looks like. And so that's Capella, the eye of the goat. And the herdsman is Auriga. This is a constellation that you've probably seen these stars before, but unless you do this for fun or love or money, you've probably never seen that before. Okay, 513, -8. We'll go to 513. That's where we were before. Let me use my grease pencil. And down almost 10, boom. And this star is a little bit confusing, but you'll notice it's part of the constellation of Orion. And that's the name of the star right there. It's Rigel in Orion. (1410) positive 19. Cruising right along here. 14, 4, 8. So that's 1410. And positive 19. 10, almost to 20. Arcturus. Arcturus. And the name of this constellation, if you follow it up here, is pretty fun. It looks like booties, but it's Bootes, okay? Bootes is also a herdsman. So the name of the star, once again, is Arcturus. And the constellation is Bootes, where the second O is actually an umlaut. So it's not every day you get to rock an umlaut. Number 8, 553, positive 7. Just a moment here. I have to spin this carefully because if I put the hole on the stand, I'm going to drop the thing and it's going to smash. Okay. Sorry, 553 and positive 7. So we're going to go all the way almost to 6. So there's 5 hours and there's 6 hours. And then we're going to go up to positive 7, which is almost at 10. You guys know what that star is, right?
Betelgeuse.
Hey, students, can you hold on? There's a knock at my door and I'm worried it might be a maintenance man. Hold on a sec, sorry. Just a minute. Sorry, buddy. Hi, you're working that light? Oh, that's awesome. Come on in. Don't mind the class in the middle of the thing. Sorry. Make yourself at home and do whatever you gotta do. I just have to, I'm almost done, but I have to keep going to this class. Thanks, bud. I really appreciate it. Hey guys, sorry about that, but it's great to get some help when you can. I had to take a moment there. Okay, sorry, we were just at 553 and positive 7, right? And you guys know what that star is, right?
Betelgeuse.
Betelgeuse. And what's the constellation?
Orion.
Very good. All right, so let me help you spell that here. Betelgeuse. And the constellation is Orion. 1627 and minus 26. Okay.
Professor, when you go to measure, can you just show us where the spring equinox is each time?
Oh, sure. Yeah. What we can do is we can follow the hours. Now, this is going to be a part of our next section. Do you guys see this circle here that has a number of dates labeled along it? This is the ecliptic, the path of the sun. In fact, there's a little nubbin up at the top of this globe, and the little nubbin will rotate this yellow sun along the dates of the ecliptic. You'll notice that the angle between the ecliptic and the celestial equator is 23.5 degrees, as it should be. That means if we're over here near October, this would be the fall equinox. You'll notice the fall equinox is at 12 hours of right ascension. That should tell me that the spring equinox, is where the ecliptic meets on the other side. So here we are, April, there's March, and bam, 0 hours of right ascension is right there. This whole line is 0 hours of right ascension, but the spring equinox is right there. Let me get my grease pencil again. Okay, so what we're doing is, and they've labeled the hours from 0 hours. This is 0 hours. There's 1 hour of right ascension, 2 hours of right ascension, 3 hours of right ascension, 4 hours of right ascension. Does that help there? Was that Fred who asked me that question?
Yeah.
Yeah. Is that telling you what you want to know, Fred?
Well, that's what you're doing, right? Going from that 0 and then counting to get the right ascension?
Yeah, but I'm skipping a few steps because rather than count every time, they've actually labeled the hours of right ascension here. And maybe I've been going too quick, Fred. I'm trying to strike a balance between getting her done and having you guys follow me. I'm not counting exactly from the spring equinox because I'm just looking up the hours of right ascension on the globe. Do you see?
Yeah.
So for instance, if we have to go to 16 hours and 27 minutes, 13, 14, 15, rotate. Actually, it's kind of good if I go at an angle here. Sorry, guys, I'm trying not to drop and break this thing. So there's 16 hours of right ascension, right? And then it's 1627, which is basically halfway between 16 hours and 17 hours. That's like 1630 right there, right? And now our declination is negative 26. So I'm starting at 1630 or so, minus 10, minus 20. I have to stay along. Okay, here I need to stay along a line of constant right ascension. So if that's 1627, minus 10, minus 20, and there's minus 26. Can you guys read that?
Antares?
Antares. Antares means anti-Mars. It's a famous red giant star that was often confused with Mars. So the Greeks named it Antares. Anti-Aries, right? Okay. Now, what constellation is Antares a part of? Where are you, Antares? Do 16. Okay. So if we follow this, we cannot cross the dotted blue line here. This is part of this constellation, which is Scorpius, okay? Antares is the stinger of the scorpion. And our last coordinate here, excuse me, our last coordinate is 1836 and positive 39. So we'll rotate a little bit more on our globe here. Here we are, 1820, 1840, that's 1836. And I'm sorry, what was the deck, guys?
Positive 39.
Plus 10, 20, 30, 39. What's our star?
Vega,
And what's our constellation?
Lyra,
Lyra the harp. Vega is the handle of the harp. So these are the 10 brightest stars in the northern sky. All of these are visible from the Margaret Jacobi Observatory, and you can find them all. Maybe if you come out and visit me some Wednesday, we can do that together, okay? Okay, so this was the major module that we're going to do, and I've just got a couple more quick little fun things just to kind of round it out a bit. You guys notice that the stars are printed on the globe, but the planets are not. Is that obvious to you guys why the planets wouldn't be printed on this globe?
Yes, sir.
What is it? Tell us, Lionel.
The planets are not constantly in the same place. They also orbit around the sun.
Right. Unlike the stars, which kind of stay locked with respect to each other, the planets drift or wander night after night. Each night, the planets will have a new position, and that position will have its own right ascension and declination. To do this, we can go to an ephemeris table, and an ephemeris table will kind of look up the coordinate positions of the right ascension and declination each night. Now, I'm going to highlight Mercury through Saturn, okay? And so let's just jot these down here. I'm not going to worry about seconds of right ascension, and I'm not going to worry about arc minutes and arc seconds. We're just going to get a rough loosey-goosey listing here. Our goal is to first look these coordinates up and then to determine in what constellation does each planet appear tonight. So using a ruler, I'm going to mark off a little section of this for right ascension and declination. That's probably good enough there, okay? So let's label the RA and the DEC so that we have those coordinates for, and this ephemeris is giving me the coordinates for tonight, okay? So for Mercury, our right ascension is 20 hours and 7 minutes. The declination is negative 17 degrees. Venus is 1847. Declination is negative 16 degrees. You'll notice that these two objects are pretty close to each other. Mars is 18 hours and 4 minutes and negative 24 degrees. Jupiter is 22 hours, 32 minutes, negative 10 degrees. Saturn is 2110, negative 17 degrees. our goal for this little module is basically just to determine in what constellation do these planets appear tonight. So we'll see if we can crank this out pretty darned quick. Okay, so 2007 and negative 17 degrees. Here's 20 and 7 minutes is a little bit past. And I'm sorry, what's the deck, guys? Can you read that to me? I'm far away.
Negative 17.
So let's see. Minus 10, minus almost 20. It looks like it's in Capricornus, according to this globe. (1847) negative 16. 1847 should be 3/4 of the way. And sorry, negative 16 degrees. Minus 10, minus 20, and back a bit. We are in this constellation. And this constellation is actually Sagittarius. Sweet. Mars, 1804, negative 24. 1804 minus 10 minus 20 or so. Let's be careful here. Looks like we're still in Sagittarius. Did I do that right? Am I crazy? 1804 and negative 24. 1804 minus 24. Yep. We're still in Sagittarius. Sagittarius actually spans a pretty good streak of right ascensions. Sagittarius is a big constellation. Are you guys noticing something about the seemingly random constellations in which the planets appear? What do these constellations have in common, friends?
They're all part of the zodiac.
Booyah. Does that make sense to you? Yes, because as one of our students pointed out today, the ecliptic, I think it was Paige, the ecliptic is the zodiac. And the ecliptic is also the plane of the solar system. Makes sense that we'd find planets there. Jupiter is 2232 and minus 10. So 2232 minus 10 puts us in Aquarius. Last, Saturn, 21 hours, 10 minutes, and minus 17 degrees. So 2110 minus 10. What was the deck, guys? I'm stupid, I'm forgetting.
Negative 17.
So over there puts us in Capricornus again. Okay. Before we move on, we have one more little module left, but I want to talk to you guys about some real ass astronomy stuff, okay? The Earth does not maintain a perfect fix. The ecliptic does not maintain a perfect fix in space over time. And that's because the moon exerts these gravitational tugs on Earth that cause it to go through something called precession. And I wonder if, do I have my little spinning top here? Yeah, actually, guys, hold on. Let me get my dreidel. One sec. Okay. Earth undergoes a motion that we call precession. And if you've ever used like a spinning top, let's see if we can do this here. Do you see that motion there where the spinning top kind of gyrates in space? That's something called precession. And because of, ooh, see this ring is kind of loose, that's causing some funky motions. Let's try this one instead. Yeah. So there you go. That's precession. Earth is actually doing this because of these little torques that the moon exerts on Earth. Except the precessional spin of Earth takes 26,000 years. And that means over a 26,000 year cycle, Earth is going through these precessional gyrations that shift the positions of the ecliptic relative to the background stars. Okay, what does that mean? It means that over time, more than the drifting of the stars themselves, we need to correct the coordinates of stars for something called processional drift. Now, this globe, this celestial sphere is actually really badass, and they don't make them like this anymore. You'll notice this was made in 1967 by the Triponese Planetarium Company in Saginaw, Michigan. 1967 is quite a few years ago, right? Now it's 2022. And over a 50-year time span, there is a relatively significant shift in the positions of stars. This is where we found the planets located according to a epoch 1950s coordinate system, which this is based on. These were printed based on 1950s coordinates. Today, our modern ephemeris gives us a better estimate of the constellations in which they appear. And you'll notice that because of precession, the actual constellations that were found in tonight are a little bit different, right? For instance, we've got Mercury in Aquarius, Venus and Mars in Capricornus, Jupiter is in Pisces, and Saturn is in Aquarius. So those are the actual constellations that they're found tonight. And that's caused by processional drift. Now, I don't mind if we have the 1950s ones down. This was an exercise in learning stellar coordinates, but I thought it would be cool to kind of explain that to you for another important reason. Let's do one more little 5-minute exercise here, which I think will be fun. Actually, you probably already know the answers to these. In table 3, we've been asked to find the right ascension and the declination of these 4 seemingly random dates on the celestial sphere. Does this sound at all familiar to you guys? Man, what
So
a
the
good
equinoxes.
Equinoxes.
and solstices. And I think this sounds like something we did in lecture. I must have been trying to give us a hookup, huh? Do we know what the values of these should be before we even look at the globe? Here's the spring equinox, right?
0.
Yeah? Tell me, guys.
It's 0 hours and 0 degrees.
So we write the right ascension like this, 0 hours, 0 minutes, like a military clock, and 0 degrees. Okay, keep going, guys. Fill in the blanks so we can do this quickly.
Summer solstice would be 600 hours with 23.5 degrees.
Yep, positive 23.5, as Caitlin told us earlier. The September 21st, the fall equinox. Talk to me.
12 hours.
And the deck?
0 degrees.
Winter solstice?
It would be 1800 hours,
And
negative 23.5 degrees.
excellent. Now look, why don't we humor them and we'll do today's date, and I want us to do one more after that. So today is January 25, right? 125. Let's see if we can move the sun to that position along the ecliptic here. So here I am, January 5th, January 10th, January 25th, okay? If we get our parallax right, the sun should appear basically right there. Can you guys tell me, are you good enough now to tell me what is the right ascension and what is the declination of that point? Someone impress me with their knowledge of the equatorial coordinate system.
Wouldn't it be, I might be wrong, but wouldn't it be 0 hour for the,
No, because the hours of right ascension are listed up here.
oh,
This
my
is the
bad,
20th hour, and this is the 21st hour of right ascension.
my bad.
So
So
we're,
it'd
Would it
be
be-
around 20 hours?
2020 is that tick mark. Let's see if let's say I try to do this wicked careful, okay? I'd say it's even 4 minutes after that. So
Okay.
2024. And obviously this is tough to do through a camera. So, you know, we have to do the best we can. How about the declination? Here's a hint. That's the celestial equator, right?
19, negative 19.
Negative 19 degrees sounds great. And by the way, we can fact check this using our ephemeris table. Let's see how we did, because we have the true answer here, thanks to these modern models. The sun, the very first one, has a right ascension of 2032 and negative 19 degrees. That's 49 arc minutes, right? So that's closer to negative 19 than negative 18. So how did we do? How was our accuracy is your closeness to the true value. Our declination was pretty much spot on, right? To the best of our measuring ability. How off were we in right ascension?
Like 5 minutes.
Yeah, 5 to 7 minutes or so. Okay, that's not too bad. Considering that each tick mark has a resolution of 4 minutes, I'm impressed with our skills. Okay, remember how I told you guys about that processional drift? You know how like the astrologers, the people who worship that shit, they like to talk about your sun sign. Those dates, though, your sun sign is based off of Ptolemy's Tetrabiblos, a book that was published around 50 AD, okay? And guess what? That was 2,000 years ago. Over the course of 2,000 years, the 26,000-year axis precession of Earth has caused the sun's location to drift significantly with respect to the background constellations. So here's what I want us to do for our final exercise, a little divination here. First, I want you guys to put down your B-day, just like we did above, as a month/day. For instance, my birthday is, I kid you not, 4/20, okay? So put your birthdays down just like that. And then I want us to make two lists. So then there's what do we call it? Your fakes, how do I put this? You know, like if you look up your sign on CoStar, your supposed sign, I'll put it that way, okay? For instance, I think my supposed sign is supposed to be like, I don't know, like a Taurus, right? But then if you actually go and check in what constellation was the sun on your birthday, you discover, if you guys go along the dates of the ecliptic, that April 20th was actually in the constellation Aries. So in fact, they told me that I was a Taurus, but on the day of my birth, the sun actually appeared in Aries. Did I spell that right? I never spelled that right. A-R-I-S, sorry. Well, okay, let's have you guys try. Fred, what's your birthday?
9/11.
Nice. 9/11. Okay. So September 11th. And what's your supposed sign?
Virgo.
Virgo. And here we are at September 10th. So September 11th should be just past there. And if we are careful not to cross any dotted blue lines, in what constellation was the sun located on your birthday?
Leo.
Leo.
So Fred, you're a Leo now. How about David? David Bruins fan.
My birthday is April 24th.
Okay, so you're pretty close to me. And what are you supposed to be, a Taurus as well?
Yes.
Well, here you are, April 25th, and just like me, sorry, you're in Aries now, okay? And I want you guys to put this down. Let's find out, how about Paige? Paige, what's your B-day?
September 23rd.
And what are you supposed to be?
A Libra.
Okay, so let's go around
my
to
God.
September 23rd. Okay, so this is close to the fall equinox. If you are there between September 21 and September 23rd, sorry, there's September, 15, 20, 25. So September 23rd is around here. What constellation was the sun in on your birthday?
Virgo.
So Paige, you're a Virgo now, okay? Josh, how about you, bud? Let's just do everyone because it'll give us a good range of dates here.
On March 23rd.
Okay, so March 23rd, and what are you supposed to be according to CoStar or something like that?
Supposedly
right?
I'm an Aries.
So, all right, but actuality, if we go along the ecliptic, if we go to March 23rd, in what, so let's put the sun there so you can see this. So there's the sun, March, you can see March 10, 15, 20, 25, there's March 23rd. In what constellation was the sun located on your birthday? Josh?
It looks like Pisces.
Yeah, you're a Pisces now, okay? How about Rachel? Rachel, we're glad to have you back for some astrological divination. What's your birthday again, Rachel?
August 22nd.
And what's CoStar say your sign is?
Leo.
Okay, so if we go to August 22nd, okay, now this is interesting. You'll notice that on August 22nd, the sun is actually still located in the constellation Leo. So Rachel, CoStar did not lie to you. Now, it does not mean that there was no precessional drift of the sun. What's actually happening, if you guys can see here, is Leo is a big ass constellation. It's like a sphinx, right? And it stretches maybe 3 or 4 hours of right ascension. So probably in Ptolemy's Tetrabiblos, the sun would have been over here at the tail of Leo, and now you've drifted over towards the paw, but you are still in Leo. So I guess
that's so you mean the constellation is as big as our egos?
that's impossible. I don't think the celestial sphere could hold it, Rachel. Okay, so what's the moral of the story? Well, you know, you are allowed to believe anything you want. It is okay to be, well, I'm not saying it's okay, but it is legal to be a crazy person, okay? No one can sort of arrest you for being crazy. But if you are interested in, you know, being consistent in your logic, your sun sign cannot be the sign that the sun had better be in the constellation that represents your sun sign. Otherwise, you don't make no sense. So to be honest, it's all bullshit, but you know, that doesn't mean I'm going to stop you in believing what you want to believe, of course. Anyways, I hope you enjoyed our lab today. The things that I want you to turn in are let's see here. The first page with table 1 and 2, and the second page. And those of you who are watching the video later on, you'll probably have a good time watching us do this. And I tried to pick a bunch of different people to get a span of dates. But either you can just fill in my birthday if you don't have a celestial sphere at home. But another thing that you could do, if you want to look up an ephemeris table, you could, if you were feeling frisky, you could type in sun to Sedna and go to ephemeris.com, and they'll actually let you put in the year and month and day of your birth right down to the hour, minute, and second, and it will tell you what constellation, what right ascension and declination the sun and all the other planets are in. So you can do even better divinations than CoStar. Remember, I require a 5% finder's fee for any fools that you hoodwink with astrology snake oil, okay? So make sure you kick back to your professor. Okay. Guys, I think that that's a wrap for today. Thanks for playing astronomy with me. On Thursday, we are going to, in fact, 1010 and 1020 are going to diverge a bit. In tomorrow's 1010 class, oh, Fred, we're not doing homework today. We do homeworks on Thursdays, okay? So Fred, until we go back in person, because we can all be together, we're all going to do labs on Tuesdays after lecture. On Thursdays, we do the lecture followed by the homework session. So for your class on Thursday, we're going to do some cool examples of finding the trajectory of the sun and stars from other latitudes. And then we're going to drift into planetary orbits and start talking about Kepler's laws. For people like Lionel, who are in my solar system class, tomorrow's lecture will be different. It'll be on timekeeping and celestial navigation and some more of the nitty gritty of this calendar.
I love all that stuff. So
It's
I'm all game.
pretty cool to learn it. Okay.
Professor, is there any YouTube animations that help us, the stuff that we learned today, that kind of visualize a little better?
Yeah, there are a couple. You know, the book that was supposed to. Bye, Mikey. Take care. Take care of your puppy. Okay. And by the way, we want to see that puppy, Mikey. You share with us sometime. Okay. There are plenty of them out there. I'll recommend a couple, but the book, The Cosmic Perspective, does have a bunch of animations. Some of them are okay. Some of them are a little clunky. I have a lot that I like for basic physics lectures, and I love the PhET simulations. I can't remember which university runs these PhET simulations, but you're going to see me using them from time to time. Unfortunately, they were all based on Flash, and they've since decommissioned Flash. Physics PhET simulations. I think they have some for astronomy too. I love the ones for physics, are really cool. But honestly, there is no substitute for reading, like reading the book. So someone recently sent me a link to, I guess these don't have any as many astronomy based ones as I would like. Or maybe this is one of them here, actually. Okay, cool. So these, I actually, simulations, it's funny, actually. Okay, fine, I actually do have these. Copy. Let me put these into the chat. I haven't gone through these extensively, but if you guys find some cool stuff that you like, you can tell me about it. Next class, we're going to be doing planetary orbits. There is a fun little simulation video game called Super Planet Smash. This will be relevant later. You can actually develop your own planetary orbits and see if you can get two planets to crash into each other. You'll discover it's a lot harder to do than you think, right? Actually, they have some famous solar systems here, and you can like adjust the trajectories of the planets and see if you can get them to bump into each other. It's not as easy as you think to do. Anyways, there's a bunch of, there's probably bazillions of cool things. Those two links I gave you are some that were recently shared with me, but I probably could spend more time going through this stuff than I do. As we go on, you'll see that I have a few special simulations that I really like that I'll be sharing with you guys. By the way, I was supposed to grade your homeworks on Sunday, and I was naughty. I did not get that done, but rest assured, probably today, I'll be catching up to the grading, okay? So make sure your homework one is in, make sure your lab one is in, and I expect to see lab 2 in, if not today, for those watching the recording later, get it to me by Sunday, okay? Okay, I'll see you guys on Thursday. I'll send you a link around 11:30. Lionel, you're in 1010. I'll see you tomorrow at 11:30. And Rachel, I'll try to remember to include you in the links if you're around and want to join us, okay?
Hey, I found out that our equator in miles is 24,901 miles.
That's great, but why would you be using ugly fucking imperial units? Like,
I'm
not
just
cool,
saying, and
bro.
it was a nice little challenge. It was a nice little challenge they had in a video game, and I took it.
Actually, I think there's a problem in one of our problem sets where we calculate, you know, how many kilometers is a degree of latitude and an arc minute, an arc second. I don't know. Sometimes they assign that one. We'll see what I did this year. Anyways, I got to process this video. Love you all. I'll see you on Thursday. Okay. Take care, space fans, wherever you are.
Professor?
Oh, yep.
I wanted to ask before you go, I tried to check my quote unquote real sign or whatever, and I'm not sure if I did it right because it just gave me my original sign.
Okay, well, let's find, why don't we do yours for kicks? What's your birthday?
March 11th.
Okay, and what are you supposed to be?
A Pisces.
A Pisces, huh?
Don't worry, mine was the same too, so.
Yeah,
Nope.
I think it might be right. I just want to check that I didn't enter anything wrong.
Right, yeah. And I'm curious too, because I like to see what fraction of students actually still have the same sign. It's always frustrating when I try to explain this to friends and then I'm like, oh shit, your sign is still the one that CoStar says. It kind of makes me look stupid. Sorry, so did you say March 11th?
Yes.
And what are you supposed to be again?
Pisces.
Okay. So March 11th is here. You're right on the cusp, as they say. Do you see that dotted blue line?
Yeah.
March 11th.
So it's literally just about to pass.
So it's on the cusp of Pisces, but it's also on the cusp of Aquarius.
Oh,
So
that makes sense.
right on the edge.
Would the 13th be over the line?
I think so. Now for that, we might want to actually go to ephemeris.com. Keep in mind, there's a bit of precession at work here. So my globe is for 1950s epoch coordinates, right?
Yeah, because my cousin's born 2 days after me, and so we always would get like Pisces stuff together. We don't even believe in astrology. We just thought it was funny. We were both the same sign, so it would be really funny if we actually weren't.
Yeah. Oh, yeah, that would be great. So did you try this here? What's the year, if you don't mind me asking?
1997.
Okay, and what's the month?
March.
Okay, so 3. And the day?
11th. And I don't know the hours or.
Yeah, who cares about that? So let's, what do I do? Do I just hit enter? Get ephemeris. Okay. Yeah, actually, according to this, it has the sun in Pisces.
Yeah.
But like I said, my globe showed you very close to a Pisces Aquarius cusp. So, and you said it was that versus the 13th, right?
Yeah, that's my cousin's birthday.
Yeah. Let's try changing that to the 13th and find out. It's probably, so one of the rules of thumb is the sun drifts by 4 minutes along the ecliptic each day. So she'll be 8 minutes of right ascension off from you.
Yeah, so she's probably right on the border.
Yep.
When she was born.
Well, so I guess you don't have to throw out those Pisces months.
I guess I don't have to throw out all that stuff, all those Pisces necklaces. That's good. I won't have to break my cousin's heart. All right, thanks, Professor. I just wanted to check.
Oh yeah, totally. And by the way, anyone watching the video later that wants us to find out, if you're watching the recording later, text me. I'll tell you, we can look it up together, whatever. I'm down to talk about this stuff. I have a good time doing it. All right.
Okay, I can't buy anything with my sign on it. I have arguably the worst name.
Well, I'll tell you what I tell people when they ask me what my sign is. I say, I'm a Vulpecula. What? And I'm like, it's a very exclusive constellation.
It's okay. I say I'm a Cancer, and they're like, oh, sorry.
My dad's
Sorry.
a Cancer too. He has the same reaction.
Yeah, I'm like, whatever.
Well, remember, there's 88 constellations to choose from out there. You don't have to choose one that the sun drifts through. Anyways, I'll catch you guys on Thursday, okay?
Thanks, Professor.
Peace.